Number 27 on sapling. So what this says, it says draw the expanded structural formula for the following condensed formula. Draw all hydrogen atoms. So this is what it's giving you. CH3, CH parentheses, CH3 parentheses, CHBr, CH2, COOH. So that's the condensed formula. They want you to write out the expanded structural formula. Right? So it wants to see the bonds. So the way I do this, the first thing I'm going to do, it's not going to be the first time you hear me say this, I number my carbons. Number your carbons. All right, so you have carbon 1, 2, 3, 4, 5, and 6. All right. 5. That way you don't lose a carbon, which just tends to happen in these cases, and it also helps keep track of how many bonds everybody has too. Right? So the first thing I'm going to draw out, which side do you want me to start from? Left side or the right side?
Left side.
Left side. So I'm going to draw out carbon 1. It says it's CH3. That's carbon 1. What other one do you think carbon 1 is bonded to? What other carbon do you think it's bonded to? 2. So I'm going to draw carbon 2. And we know for a fact, what else is 2 bonded to?
3.
It's also bonded to carbon 3, that's correct. So let's go 2 and 3. What else is bonded to 2? So it's missing some bonds, isn't it?
Isn't 3 coming off 2 but not to 3? Or not to 4? Like 2 goes right to 4.
Well, so what else is bonded to 2? Let's just work about where else is bonded to 2 at this point.
Hydrogen.
There's a hydrogen. Let's put a hydrogen bonded to 2. So right now 2 only has how many things bonded to it? 3. So something else must be bonded to it. So this parentheses here indicates, right, that this is bonded to 2, but 4 is also bonded to 2. So the parentheses here segregates that essentially methyl group, that CH3, and indicates it's bonded to the thing just to the left of it, the carbon. So what else is bonded to carbon 3? In the parentheses it has 3 H's, right? So we need to have the H's there. So now carbon 3 has how many bonds? It can't have any more bonds, right? So what else must carbon 2 be bonded to?
Carbon 4.
Carbon 4, right? See the parentheses here? So there's a CH2 here. Parentheses, this whole thing is bonded to the carbon. And so is this carbon. So carbon 2 is bonded to this whole group through this carbon. See that? So now 2 is bonded to 4. What else is 4 bonded to?
2.
2 and hydrogen and a bromine and a end. It's only 3 bonds for carbon 4. Now what else is it bonded to? Has to be carbon 5. So there's 5. Oops, that looks like a 6. There's 5. What else is 5 bonded to? 2 hydrogens. And what else must it be bonded to? Carbon 6. Now this is tricky here. You see the COOH. So it has to be a double bond, right? This carbon is double bonded to one of these oxygens, and the other one is an OH. This is carbon 6. We call that this whole thing is a carboxylic acid. We see the COOH, that's a carboxylic acid. Good question. How did I know that this means a pi bond? A couple of things. I see 2 oxygens that are like this, I know it's a carboxylic acid. And if I see a CO like this, I also know it's a pi bond. I see this carbon has to be bonded to this oxygen in a pi bond. You start to see it and recognize it. Looking at number 2 from the basics lab practice quiz 2014.
Yes, please.
It says, so from A, the first part, or from number 1, we found out that we have 13.71 millimoles. We'll use a lot of millimoles in this class of B. It turns out a mole is a lot of stuff, like a lot of stuff. We won't do things on that scale, so we use a lot of millimoles. So that's how many millimoles we have, and this question says, the B comes in a 1 molar solution. If we have 500 milligrams of B in that solution, how many milliliters of it did we use? So how do we set this up? What's a 1 molar solution mean? So 1 molar equates to what?
1 mole per liter.
Is equal to 1 mole per 1 liter. We could also write that as 1 millimole per 1 milliliter. Right? It's the same ratio. So how many milliliters of it do we use? How do we do it? We need to get our units in milliliters, right? So molar gives us a milliliters and a millimoles. And we already have millimoles. So can we use this number and this unit conversion to get leftover milliliters? Right, so if you know what you're trying to get, like, so right, the unit conversions, at the end of the day, just always think about what am I trying to get? What units am I trying to get to? So for this one, you would just take 13.71 millimoles of B, and we have it in a, I'm just going to erase this quick, maybe not. Not going to let me? It's fine. I'm going to shrink it down and redraw it. So 13.71 millimoles of B, and we have 1 millimole per 1 milliliter. That's the 1 molar conversion. Cancel. What do we end up with? 13.71 milliliters. Looking at number 28. And this is about determine the hybridization and geometry around the indicated carbon atom. So I'm just going to draw this out. Perfect. And now I'll point out which ones they're talking about. They have A, B, and C. So they have, this one is A. They're pointing as this one as B, and they're calling this one C. So hybridization has to do with how the molecule, how that element, that particular element is bonding. Right? The easiest way to look at this is, the first question you need to ask yourself is, does this element have pi bonds? All right, so the first question you should ask yourself, does it have pi bonds? Right? If it has pi bonds, so pi bonds, if yes, then it must have what kind of orbitals? If you have pi bonds, you must have what type of orbitals? That's a hybridization state. So don't confuse hybrid states with hybrid orbitals. So if you have a pi bond, what type of orbitals make up a pi bond? Remember, this is a pi bond, the face-to-face. What kind of orbitals make up pi bonds? P orbitals make up pi bonds. There's no such thing as a pi orbital, and there's no such thing as a p bond. Pi orbitals, whoops, there I did it. Pi bonds are made up of what? P orbitals. Right? this is I'm drawing right here a pi bond, and this is a p orbital, which helps make up a pi bond. So if you have a pi bond, you must have a p orbital. Yes? So let's do the hybrid states. What are the hybrid states? What's the first one, the most common one? sp3. Right, so sp3 is a hybrid state. I'm going to put a box around it. That's a hybrid state. What kind of molecular orbitals does an sp3 hybridized element have? It has 3 sp3s. Now I'll go into more depth in this tomorrow. Right, but you should know this from Gen Chem. What's another hybrid state? sp2 is a hybrid state. What kind of molecular orbitals does sp2 have associated with it? An sp2, an sp2, an sp2, and a p. How many pi bonds can an sp2 hybridized element have? How many p orbitals does it have? How many p orbitals are right here? How many p orbitals of these four things? I'm looking at this. There's an sp2, 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 and a p. How many is that equal for p's? 1 p. Right? How many p orbitals are there right here? Just the one. So how many pi bonds can that make? Just the one. Right? So it can make 1 pi bond. An sp2 hybridized element can only make 1 pi bond. Another hybrid state is sp. The molecular orbitals associated with that are sp, sp, and then 2 p's. How many p orbitals does an sp hybridized atom have? 2. How many pi bonds can it make? 2. So at least we know that. We'll talk about where we get these hybrid orbitals from later, but you can take my word at it right now. These are the facts. So for every pi bond, we can only have 1 p orbital, right? 1 p orbital gives us 1 pi bond. So A, that carbon A, how many pi bonds does it have? This carbon up here, A, how many pi bonds does it have? Does it have any? So what hybrid state must it be? Has to be sp3. All right, so that's sp3. What about B? How many pi bonds does B have? 1. So what hybrid state must it be? sp2. Right, because sp2 has 1 p orbital, which can make 1 pi bond. What about C? How many pi bonds does C have? 2. So what hybrid state must C be? sp. Now there's a reason for all this, why, the shapes and different things like that, where these 4 come from. But these are facts, right? These are things you should know. The difference between a hybrid state and the molecular orbitals associated with that hybrid state. All right, so we're going to look at 3 molecules. CH4, NH3, and water. And the question is going to be, rank the reactivity of the bonds to H from high, which is 1, to low, which would be 3. Period. Go ahead and do that. Why? So how do we think through this problem? Give me some logic how I thought through this. Sure.
I looked at it from like the hydrogen bonds.
Okay, so you looked at the hydrogen bonds. So tell me more about that.
Well, what I learned, hydrogen bonds occur in nitrogen, oxygen, and fluorine.
And they.
So I looked at just those two at the right.
Mm-hmm.
Canceled out the one on the left.
So
The first one that is,
So what do you mean by canceling out? So what does that mean? Is that reactive or not reactive?
it has a low reactivity.
Low reactivity. Okay, good.
Man, I kind of went up, I wasn't sure about the other two.
Mhm.
Looked at like electronegativity. I don't know if that plays a role.
Absolutely.
So I looked at it and it said oxygen's more electronegative than hydrogen.
Yep.
So I guess that water was more reactive than
So the OH bond you thought was the most reactive, and the NH bond was the
second.
2. And you said, so it's nothing to do with hydrogen bonding. So it's nothing to do with hydrogen bonding. It actually has to do with electronegativity. Right? So hydrogen bonding actually isn't a bond. Everybody realizes that, right? H bonding is not a bond. Right? Mm-mm. And it's not a strong interaction either. Mm-mm. Right? Right? So don't worry about hydrogen bonding here. It's all about electronegativity. It's all about those polar covalent bonds. Which bond is the most polar? Because polar bonds, right, have more of a dipole, right? Where there'd be a plus end and a minus end. More polar the bond, the more reactive it is. Right? The electrons are already polarized towards one element. So a more polar bond is more reactive. And if you look at electronegativity, right, if you just looked at these things, you said, well, hydrogen's all the same for all of them, right? So I have carbon, nitrogen, oxygen. It's like, what's their relationship on the periodic table? Carbon's farthest to the left, then nitrogen, then oxygen, all in the same row. What happens as you go from left to right across the periodic table? Electronegativity increases. So that means oxygen is more electronegative. It's going to be a more polar bond, more reactive bond. Right? So find that differences between them and see where they're at in relationship, usually on the periodic table. Right? Remember I told you the periodic table has electronegativity and size. Those are going to give you a lot of the answers. Pretty much everything. Right? The periodic table has all the answers. It's all there. Good.